neutrons escape at the boundary, and so you need something surrounding it to knock them back in. That's called the tamper. He did that first, either ahead of or parallel to Heisenberg in 1939, independently. And he also got something that Heisenberg didn't get. He had the correct formula for the neutron multiplication factor, which is important if you want to know how the multiplication factor in U-235, which is about 2.5, is related to that in natural uranium, which is about 1.18. Now, in 1939, Peierls was inspired by what he thought was the flaw in Perrin's assumptions to improve on Perrin, and he made a mistake, which I'll cover. The interesting thing is that Frisch used Peierls' result with what Frisch called vastly optimistic fission, and I'll add scattering cross-section values to predict the tiny critical radius that was presented to the British to try and spur them to get moving on the nuclear bomb program. So my difference with Pete will be that it's clear to me that Frisch did this intentionally. He didn't make mistakes. He did it intentionally. I'll tell you why. Then we come to Serber's 1943 Los Alamos primer, which reproduced Perrin's and Heisenberg's 1939 formula for critical radius independently. And what he did, of course, different from them, was to insert U-235 numbers to get a critical radius for the uranium or U-235 or plutonium bomb. Finally, at Farm Hall, without any notes, books, or anything, just his memory, Heisenberg recalled his 1939 formula from memory. He re-derived it for the case of a bomb. There's a distinction between how you calculate for a bomb and how you calculate for a reactor, but the result is the same for a sphere. And he re-derived it and put in what he thought were the values for a bomb and came out with reasonable numbers at Farm Hall. So you could say that he didn't know any more in 1945 about a bomb than he did in 1939, or he could turn around and say he knew as much in 1939 about a bomb as he did in 1945, but he didn't advertise it. And the last part is that I'll cover why the higher law reactor didn't go critical and what they needed in order for it to go critical. And this more or less, this is close to, what my conclusion is close to some simulations that have been made. All right. So the question is, how do I give a completely mathematical talk without using mathematics? And on the minus side, it's going to be hard for me to be understood. And on the plus side is that everything is fixed. I'm not giving opinions, I'm just giving the results of calculations. And so, as I said, the massive equations and the slides that follow are just to remind me what I'm supposed to try to explain to you. Here are the points that I want to cover. Heisenberg's G39 paper, where he calculated critical radii for a spherical reactor tampered with mixes of heavy water and natural uranium. Second is Perrin's formula for the neutron multiplication factor. I'll cover what's essential to understand where Peierls made a mistake in trying to improve on Perrin. And the main thing of that is that I'll discuss how Frisch used that calculation without worrying about whether it was right or not to make his prediction. And then write down and describe Heisenberg's Farm-Hall formula for the critical radius of a bomb. And in the end, I'll talk about the high-level reactor, and what's shown in green here is what's new in the last couple of months that's not yet in print anywhere. So it's always nice to have some pictures, because then you don't have to think. The first person on the left is Perrin, who was an expert in gravity motion. The next is Flüge, who constructed, I believe, the Encyclopedia der Physik. The next three you recognize, maybe not Frisch, who's on the right. Oppenheimer. Serber was Frisch's right-hand man. He was in charge of, he was not, Hans Bethe was the head of the theoretical program at Los Alamos, but Serber was the one who wrote the little booklet that oriented newcomers to Los Alamos about what they were doing. It was called the Los Alamos Primer. And that's what had the first bomb calculation in it. And that calculation was actually, the primer came out in 43 at Los Alamos. But in 42, these two guys, Frankel and Nelson, had actually worked the formula out. Serber didn't work it out. Serber wasn't a lightweight, he was an expert in group theory. But these two, more or less assistants, Frankel and Nelson, were the ones who actually did it. So for historians, what is efficient chain reaction? The equation for that is just like the equation for a chemical chain reaction. The only difference is that the energy scale involved is nuclear, not chemical. And the two important parameters here, so d and dt is the rate at which neutrons in the sample are changing with time, n is the neutron density, nu is the number of neutrons released by absorbing one neutron. So this -1 means that one neutron has been absorbed and new neutrons are coming out in place of it. If nu is greater than 1, then you've got fission. Right? So that equation is fine if you're talking about a uniform sample where n doesn't vary in space, but in a finite uranium sample, there are variations of neutron density. And so to describe that, you add this this doesn't work on that, does it?
No, we can see it.
Huh?
Yeah, let's go.
You add this diffusion term, yeah. That represents diffusion, and all it does is describe how the neutron density varies due to the finite boundary. Yeah. Now, to describe the critical state, we need the steady state. The critical state is it's a not stable steady state. It's steady in the sense that the neutron density is not changing with time, but it's unstable in the sense that if you tweak it one way or the other, it becomes either it blows up into a lot of neutron production or the neutron production decays. So it's a critical state. And that's given by this equation. And if we divide through by d, we get the form that Heisenberg actually used, where this L in this 1/L squared. So this L has dimensions of centimeters. Here you've got dimensions of 1/centimeters, so you have to have dimensions of 1/centimeters here. So L has dimensions of centimeters. It's called the diffusion length. In particular, it's called Fermi's diffusion length. He was the first one to introduce it. And the formula for that is this. And if you know these parameters, d is the diffusion coefficient of neutrons in uranium. Tau is the characteristic time for fission. It's the characteristic time between two different fission events, two different neutron absorption events. And of course, nu then is this, nu greater than 1 is the neutron multiplication factor. And this length, not cross sections, is what Heisenberg concentrated on in G39. At Farm Hall, he had to worry about cross sections, but he had a table of L versus various parameters in his uranium heavy water mix, right? Now, how do we treat this problem? I'm not using, if there are any reactor engineers in the room, you can close your ears. I'm not using the terminology of modern reactor theory. I'm using the terminology of 1945. And so we're going to talk about the Laplacian. This is the Laplacian. It's the double gradient of the neutron density. It's the acceleration of the rate of change of the neutron density, if you like. And if we can satisfy this equation, then the rate of change of the neutron density in uranium is proportional to the neutron density. And this lambda is what we want to calculate, because then we can replace this by lambda n, and we have lambda equals 1 over L squared. And this lambda is calculated from the geometry of the reactor or the bomb by imposing what are called in mathematics boundary conditions, how the neutron density or the current or both change at a boundary. And so we can calculate, mathematically, we can calculate this lambda. And that's what we want to do. By dimensional analysis, lambda has also dimensions of 1 over centimeters squared, just like 1 over L squared. So if I have spherical symmetry, if I'm considering like Fermi did, a spherical reactor, or Heisenberg, or Heisenberg, a spherical bomb, then there is only one parameter, and that's the radius of the sphere. So this lambda is 1 over some number times the radius squared by dimensional analysis. You don't have to do any more mathematics than that. It's just dimensional analysis. Dimensional analysis always, if you have a sphere, it determines the critical radius within a prefactor, and the prefactor is determined by the boundary condition. If I impose different boundary conditions, I get different parentheses, dots here. Different numbers, right? So if I impose the spherical tamper as well, actually Perrin imposed a spherical tamper, but it wasn't quite the same tamper that Heisenberg used. If you use the ideal spherical tamper, which is what Heisenberg and Heisenberg used, both, what you get for the prefactor is pi over 2. So that's where it comes from. So what's in G39? There's quite a lot in G39, and I'm only concentrating on here on one section of G39. This is the report that Heisenberg submitted to Army Ordnance in 1939, which is kind of like a research proposal for the uranium program, right? For physicists to get some money to do uranium research. And it's not about bombs, it's about reactors. He mentions explosion. He uses the word explosive a couple of times, but the whole thing is about reactors, and all of mathematics is about reactors. So he's talking about, he knows that he has to have a moderator to slow down the neutrons because the cross sections for faster neutrons are too large. They get absorbed by the natural uranium. And so the moderator is heavy water, which of course they got from Norway. And that produces the slow thermal speed neutrons for the reactor. The tamper, which surrounds the reactor, is some kind of non-absorbing material. It could be uranium surrounding it, but it's got to be net non-absorbing. If it's absorbing, it's got to also emit, so it's got to have no net neutron absorption. Heavy water satisfies that, as long as it doesn't have impurities in it. So what Heisenberg actually made two calculations. He made a calculation for a spherical reactor with no tamper, and that's actually what Fermi had in Chicago. He didn't have any tamper. He just had a big spherical pile. It was a pile of graphite and natural uranium. And for that, you get pi times L as the critical radius. If you add this ideal tamper, you cut the radius, you cut it in half. The size, you cut the size needed in half. All right, so that's the power of 2. Now what's really interesting, aside from the fact that Heisenberg made this first really careful, correct calculation for no tamper and for an ideal tamper, is that he also worried about the neutron current at the boundary. The neutrons per second escaping from the boundary of the sphere, right? Because they're created inside by fission, and they're also, some are reflected back, but a lot of them are escaping. So he worried about the escape, and so he calculated the current, the rate at which neutrons are leaving. And from that, he got what he called the Fermion, the increase over the current source. In a reactor, you have to place a source, let's say, at the origin of the sphere. So you make a hole and stick some kind of a source down there, a neutron source, and the current coming out of that source, I denote here by J. This is not Heisenberg's notation, but this is closer to normal physics notation for current. So this is the current coming out of a little sphere surrounding the origin, surrounding the source at the origin. And this J prime is the current going out of the sphere at the boundary. That's what you're losing. What you would like to have reflected back in if you can. But if it's reflected back in, that will be taken into account in the value of J prime that you get. And I think I remember I followed Heisenberg's calculations. If you put the tamper around the sphere, you reduce this loss by a factor of 1 over pi. So you reduce your loss by about a third by using the tamper. But the most interesting part of this is not that he calculated the Fermion, it's that, and this is extremely non-intuitive, it's that the source current is something you're feeding, right? You've got a source, external source at the center, you've stuck it there, and you don't turn it off. It's always there in the solution of the reactor equation, but the current vanishes at criticality. The current out of the source goes to 0 as you approach criticality. You can calculate and see how far out you have to go. I've done that before it appreciably picks up. What happens is for about the first 1/6 of the radius of the sphere, there is no net contribution to fission. It's all from the outer shell. And this is non-intuitive. So what's happening, the only possibility is that what's happening is that fission is canceling the current. The current's still there. Nobody took it out. But it goes to 0. And the only thing that's happened is fission. So fission cancels the current at criticality. And Heisenberg took this so seriously that he assumed that it was a general feature of criticality independent of the shape of the reactor, which turns out to be wrong. That's where he got off the track. I said he never understood that this infinite increase in neutron current ratio at criticality depends on a spherical symmetry. It's not that, when K is infinite at criticality, and this is what he always talks about in his papers and what he looked for, it's not because the current at the boundary becomes infinite, it's not because the fission becomes infinite, it's because the source is canceled. It's 0, so it's the ratio that's infinite. Now, there's the question, how do you relate the neutrons per fission emitted in U-235 to the neutrons per fission emitted in natural uranium, which is over 99% U-238 and less than 0.7% U-235. Perrin and Flüge understood that before they understood what it was that they should calculate. They got the equation right. So this correct equation, I've written it in simplified form, as if there would only be one absorber. That's enough to illustrate the idea, right? This sigma sub A, this is the cross section for absorption, and let's say in U-238. Sigma sub F is the fission cross section, and this ratio is what reduces the neutrons per fission. It reduces it from 2.4 in U-235 down to 1.18 in natural uranium. Heisenberg did not read Perrin, and he probably didn't read Flüge, and he didn't understand this. At Farm Hall, and also later, in I think one of these Fiat reports, he thought that the way you got the one rate from one multiplication factor from the other was by a multiplicative factor, a ratio of cross sections multiplying a rate, which is wrong. And he was misled. He said, aha, it's okay. His cross sections were wrong, but the ratio was right. And so he got the right estimate at Farm Hall and later, but the correct way to do it is the way that Perrin and Flüge showed. Okay, so we come to Mr. Peierls, who had studied Perrin's paper, and what he didn't like was that the same thing that many people commented on, the mean free path, which is the average distance, it's supposed to represent the average distance that a neutron moves before it collides with another, with U-238 nucleus. It's too large compared with critical radii. And so he said, yeah, this is not so good. Many people noticed this. And so he wanted to improve on it. What he didn't think about, at least in writing, is that when you put a tamper around the uranium, neutrons are reflected back. So the fact that the critical radius is bigger, maybe on the order of the size of the uranium, is not so drastic as it would be if you don't have a tamper. Anyway, he wrote down an equation which I have never understood, and I have no hope of understanding. I don't know where he got it. I'm not the worst theoretical physicist, and I looked at this equation and I thought, what was he thinking? Anyway, he used that to derive something that looks like our reactor equation that we've written down, except it's got these parameters alpha and beta. And this alpha we understand that. That's 1 over the mean free path for all collisions. This N is it's the uranium density. Sigma sub S is the scattering cross section. That's just reflection inside the uranium of a neutron without absorption. Sigma sub A is the absorption cross section. U-235, they knew at Los Alamos. U-238 absorbs neutrons and converts them into plutonium-239 eventually, or 240. And sigma sub F is the fission cross section. So that's the normal definition of mean free path in kinetic theory. But then he introduced this second length scale, beta. And I looked at it and I thought, what is he doing? Where did that come from? If he had had a hat, he must have pulled it out of the hat, because there's no rhyme or reason for writing that down. And anyway, he got this equation, this equation that we now know the form of this from his integral equation in a certain limit. And it took me a while, but I finally realized that you can rewrite this factor, so this should be nu minus 1 over tau, where tau is the fission lifetime, right? I finally realized that you can rewrite that factor in that form with Perrine's accounting for absorption. And so it's clear to me that he didn't define beta in the beginning. He chose beta in order to match this. That's the explanation of where that length comes from. Otherwise, there's no reason in hell to define beta the way that he did. That's it. He gets the right reaction rate if he takes beta to be the way defined. Now, in the end, what's wrong is that you can see that this, if beta over alpha is equal to 1, the effective multiplication factor is 1, which means there's no fission. Fission goes out the window. But you need beta over alpha equals 1 to get the diffusion rate into agreement with kinetic theory here. So there's no way you can bring this equation into agreement with both fission theory and kinetic theory simultaneously. It's wrong. But this is what Frisch used in calculating for the Frisch-Peierls memorandum, and that's okay, because what Frisch did was choose numbers so that this factor is right, so that it agrees with fission, and then you make a little mistake in the diffusion coefficient. It doesn't matter too much. It's all right. So we come to one of the two main points of the talk, because the rest of it is a year old. And these things are since last spring, these two new points. The Frisch-Peierls memorandum, 1940. So Frisch was, if you read, I read Peierls' biography, I've read Frisch's biography, and there's also a very interesting oral history for Frisch that you can find on the internet. I have a reference here at the end, you can have it if you want. And Frisch makes it very clear that he was very, very alarmed. Right? Frisch is Austrian. He's Lisa Meitner's nephew. Peierls is German, and they're together in England, and neither one is trusted because they're both Jewish emigres, but they're not trusted because they're German and Austrian. So they're kind of outside the nuclear circle at first. And Frisch wanted to impress upon the British government, according to his biography and the oral history, that they really need to take seriously that Germany might be developing a bomb, because Germans certainly have the capability to do that. So what he did, and he describes it, was he took Frisch's model, and he didn't care too much whether some factors were right or wrong. What he wanted was to get a small cross-section to impress upon the British, a small critical radius to impress upon the British that it might be possible for the Germans to use a tiny amount of uranium to produce a bomb. So what he did was and you can read this in the Frisch-Peierls memorandum, they make three assumptions there. One is that the neutron production per fission is 2.3, 2.4, 2.3, who cares? It's close enough, right? And then he says, they write, there's no appreciable scattering. Well, this is crazy. The scattering cross-section is bigger than the fission cross-section. So they set the scattering cross-section equals 0. It's 0. And when you do that and neglect absorptions, all you're left with is fission. There's nothing else left. So the mean free path for collisions collapses onto the efficient mean free path, and the only cross-section is the efficient cross-section, which Farrell's took to be 10, but in reality, if you ignore absorption and say there's no scattering, there's nothing but fiction, you can say that the efficient cross-section is diddly. It won't make any difference because it cancels out in the equation. So it maybe mentally he said, okay, if the efficient cross-section is 10, the absorption is something, it dominates it, we'll ignore absorption, but they've already thrown scattering out the window, which is much more significant than either fission or absorption. Right? So his aim was to get a small radius. That's opinion based on the mathematics. I don't have too much opinion in this talk, that's about it. But I take that from what he has written. So he wrote, so in his own words, well, no, this is from the memorandum. I took the formula which Farrell's had published about, this is from his oral history. I took the formula which Farrell's had published on the critical size of fissile material, and I put in a vastly optimistic figure for the fission cross-section, 10 instead of 1/2, which was what was known at that time. 20 times larger than what was known in 1939. And came out with a critical mass of 1 pound. He got, the formula he got was that the critical radius is 8/10 of the mean free path of U-235. And to date, as far as I know, nobody has figured out where the 0.8 came from, but I have calculated it exactly if I round to 2 digits. If you calculate using his partial differential equation, not the integral equation, or what would be the lower graph, not the upper graph, lower curve, not the upper curve, in Farrell's graph plot of his solution, then you get R as 8/10 L, and if you take L to be 2.6 centimeters, which also is wrong, but doesn't matter, you get 2.1 centimeters out as the radius, which is what they predict. So there is absolutely no mystery about where he got the prediction. So now we come to Heisenberg at Farm Hall. As far as I can see, he only worried about reactors. And he worried mainly about reactors in 1939. I've seen some papers later than that. Some papers we did calculations. There are actually some papers we did calculations using his fission reaction equation. But the only thing, nothing really new so far as I can see after 1939. So what happened at Farm Hall? At Farm Hall, when the group of 10 was faced with the fact that 2 bombs had fallen on Japan, and they decided, okay, it's not a news hoax, it must be true. They asked 9 of them, including Weizsäcker, who was also a theorist, asked Heisenberg, how is it possible? So Weizsäcker didn't want to calculate. So Heisenberg went away, I think, for 8 days. He didn't have any books, no notes, no references, and this was 6 years since he had submitted G39. And there, he had worked out a solution for a reactor, which contains the neutron source at the center. But remember, the neutron source is canceled, so what you're going to expect is that the critical radius for a bomb is exactly the same for a sphere as for a reactor, if you have the same temper, which it is. So he went away, and from memory, he wrote down his equation, and he calculated for a bomb, which means with no neutron source at the center. It's a different solution. In the end, the critical radius is the same. And so it came out, he probably said to himself, I sort of see that in the Farm Hall report, yeah, we're able to get there with our reactor equation. There's nothing new. It's kind of like he's surprised when I read it. You can read the German and see what you think, but it seems to me like that. There's a little bit of no surprise in it, but the same thing comes out. And the only thing was he didn't know the fast fission cross section any better in 45 than he did in 39 because they hadn't done any research that gave him a good number. So what he knew in 39 was from some measurement that it could be half a barn, and the geometric cross section is 2.5 barn. So he calculated only for a tamper in this case, and of course he got exactly the same critical radius as he did in 39 because not having a neutron source doesn't matter, it's canceled. He calculated for a tampered sphere and he came out with that. And he knew, he had heard somewhere from American reports that there should be about 2.4 neutrons. Actually, what he did in this at Farm Hall was to scale up to 1.18 using his wrong multiplication formula, and he got 2.4 by accident because the ratio of the cross sections was just right. The cross sections were wrong, but the ratio of cross sections was right. So by a wrong method, he arrived at 2.4 from 1.18 at Farm Hall. He didn't know it was 2.4, but he did know that he was dealing with fast neutrons. He took the velocity of neutrons to be the light speed divided by 20. Los Alamos took light speed divided by 10. He took light speed divided by 20. He understood. It was fast neutrons. No discussion. All right, so you can say he hadn't learned any more about calculating for a bomb than he knew in 39, or you can say he knew as much in 39 about calculating for a bomb as he did here, and he did it correctly here, aside from efficient cross sections. There they are, there are the numbers. And he, with his, Spaltman square Schnitt, he took half to 2.5, Los Alamos took 1.5 barn, and notice that 1.5 is halfway between half and 2.5. So he got, as the critical radius, he actually got a critical radius smaller. The arithmetic was wrong. In the Farm Hall report, he did the arithmetic wrong. When I calculated, I get 4.7 centimeters to 9.5, and he had much bigger numbers. What they calculated, Los Alamos was 6 3/4 centimeters. So he didn't pull it out of the hat. He knew how to calculate for a reactor or a bomb. But the only calculation he'd done before then, as far as anybody knows, was for a reactor. He wasn't the world's worst theorist. Now, I think I have time, don't I? Okay. What they had at Heisenberg was not a sphere, it was a cylinder. You use the same equation, the reactor equation, and you use also the idea that the Laplacian is a factor times the neutron density, that's this, and you get the condition that the Laplacian, the inverse square of Fermi's diffusion length, has to match this parameter lambda, which for cylindrical symmetry is the sum of two mathematical separation constants. Technically, this equation separates in cylindrical coordinates into separate solutions for radial and axial parts. And this is the separation constant for the radial part, that's the separation constant for the vertical part, the axial part. And so what you get is for criticality, at criticality, these two have to match. At criticality, the Laplacian has to be some number which we don't yet know times divided by the radius squared plus some number we don't yet know divided by h squared. And these two numbers, little r, little g, are determined by the boundary condition. And we're going to follow Heisenberg and impose the full tamper. They had a full graphite tamper around the Heisenberg reactor, which you can see here. This black with slanted lines is supposed to be graphite. These cubes of uranium are hanging on metal strings, and in between is heavy water as moderators. That's the sketch from Heisenberg and Wirtz, I think it's 1946. And so we have a full tamper boundary condition, and Heisenberg never calculated that. What he did was different. Well, this is what the reactor actually looks like. You can see the graphite bricks, or this gray material is supposed to be the graphite bricks. I don't know if it was real graphite, if they left it there or took it out and replaced it by somebody else. And here's the uranium simulated hanging on cubes. Now, the funny part. That reactor was designed as what I call a spherical cow. How many people know what a spherical cow means in theoretical physics? Quite a few. I'll tell the rest of you. When a theorist, the joke is in theoretical physics, when you meet a problem that's too difficult, let's say the shape is too difficult, you don't know what to do with it, you approximate it by sphere, and so we call that the spherical cow. Now, the Germans built a spherical cow because the height is twice the radius. The sphere of radius r fits inside the cylinder perfectly. I think it must have been intentional, because Heisenberg knew how to calculate for a sphere, and he never calculated for a cylinder. But you can calculate exactly for a cylinder without making it a spherical cow. Nevertheless, so this is described in what he tried to calculate is described in this Fiat report. Well, it's 1946 or so. I have the references at the end. He describes what he did, and his calculation is a mess. He's using spherical ideas with axial calculations. It's mixed up. But he's trying to use what he knew before, and the main thing that he knew from earlier is that the source is canceled by fission at criticality, and in the cylinder it is not. So he's way off. So they have a spherical cow reactor, and he made a spherical cow calculation. But somehow the dimensions of this reactor are correct, and I'll explain to you why. They're not wrong. The dimensions of the reactor, without any theory, correct theory, as a guide in construction, the dimensions are correct. By correct, I mean it could have reached criticality. So here's the Laplacian, 1 over L squared. If you calculate for a full radial tamper, you get this factor of 1.15. And here, to find out what that is, I have to impose the vertical tamper. Top and bottom have also equal thickness of graphite. So you can see from this, if they're Laplacian, well, this is the length. I should have called it L here. I wrote L1, it's L. He took 35 centimeters, and I couldn't see where he got that. So I wondered, this was the fine ointment. I didn't know if this 35 centimeters really made any sense physically or not. But if you take that, you get 1 over L squared. is 8 times 10 to the minus 8 centimeters, or it's about 800 times 10 to the minus 6. They needed 2.2 times 10 to the minus 4th for criticality. You can, just by putting the value for this and using the radius, you come out that this is what they needed. But they didn't have enough heavy water. They had enough heavy water to fill, what, 60 or 70% of the kettle, and not more than that, because the rest of it had been contaminated. And they had access to it, but there was no use. They didn't it was not transported to higher level. It was sitting in wherever deemed it was, intuitively. So they needed that, and with what they had, it was 4 times 10 to the minus 4th, which is, if you've got a bigger number here than what they needed, then it's subcritical. So it was way subcritical. It wasn't even close. If you would assume that they had a full tank of heavy water that was filled to the top, you get 2.5, which is really close. So the prediction is, from the diffusion theory, which Heisenberg could have calculated but didn't, that the reactor was either nearly critical or was critical. There's a second boundary condition Heisenberg imposed. He talked about an albedo boundary condition. That's a way of representing a tamper, but you need a parameter in it, which they could have measured. It's a diffuse reflector. It's not a good reflector, but it's a way of approximating a tamper. If I use this tamper boundary condition, I calculated for that, I come out that the prediction is that it was slightly critical. So one calculation is slightly sub, one other calculation is slightly supercritical. So they were close. Now, that's not all. There was a letter which I am really grateful to Heisenberg for sending it to me. 1945, Weinberg, who was one of the 2 fathers of reactor theory in the U.S., along with Wigner and Nordheim, were asked to evaluate the German program and report to Compton. And here's what they wrote in quotes. I just took certain quotes from the letter. We're writing to correct what we believe to be a very prevalent misconception concerning the state of art as known to the Germans in 1945. The Laplacians, now you are all educated, you know what a Laplacian is. It's Fermi's inverse square diffusion length. The Laplacians are of the order of 1,000 times 10 to the minus 6, which I just mentioned. This value is an excellent agreement with ours. 1,000 times 10 to the minus 6 is a 32 centimeter diffusion length instead of 35 centimeters. Very close. Generally, we would say their approach was in no wise inferior to ours. In some respects, it was superior. The fact that they did not achieve the chain reaction is primarily due to their lack of sufficient amounts of heavy water. So I just made a calculation which backed up. If whatever calculations they had were classified and probably remain classified. I don't know if they were ever declassified, but nevertheless, the one I made this spring is the only one I know of. So, and the other funny thing is that Wirtz, I'm nearly finished, Wirtz met Weinberg at a heavy water meeting at the EFEC reactor in Kjeller, Norway later. And he was surprised how much Weinberg knew about their program. He just remained surprised. That's in Wirtz's book. And then later, he was invited by Weinberg to visit Oak Ridge, 1965, and by accident, the letter to Compton was lying on a desk And Wirtz read it, and he said he was really surprised that the Americans gave the Germans higher grades on the reactor program than they would have given themselves. So, I ended here, I have calculations. If you take an infinitely long cylinder, tampered, you've got a critical radius of 1.5 times the diffusion length. If you take a fully tampered sphere, it's 1.57 times the diffusion length. If you take a fully tampered right circular cylinder, which we just considered, it's 1.8 times the diffusion length. And if you take Heisenberg's spherical calculation at Hyderlock, it's 2.29. Heisenberg said in the end in 1946, we needed about 1/3 more uranium. He didn't. And that's what Weinberg and Rhein also said. I have references in case anyone wants them.